Nice. So we're live. It's very nice that we have everything on time. Okay. All right. And this is Dr. Ting, and this morning I'm going to talk about the Wuhan coronavirus. Okay. And that's the hottest topic here. So just before I talk, I need to remind all my friends in China, in Taiwan, in Hong Kong, in Singapore, that Wuhan coronavirus can be cured. You just have to take lots of vitamin C, okay? And if you have got high fever, take 10 grams of vitamin C every 4 hours until you get diarrhea or until the virus is subdued. Okay, so this is very effective. And then, sorry about this flu. For our American friends, this is still a flu season, and lots of people are getting the flu. But I think they estimate 6,000 people died every year due to the flu. But the flu can be cured by taking 5 grams of vitamin C every 4 hours. The symptom of flu is much less severe than Wuhan virus. So, probably every 4 hours, 4 grams would kill you. So,
is it just off-the-shelf vitamin C? Or
any vitamin C, yeah, just vitamin C. So, how does that work? Yeah, if you take enough vitamin C, it will kill all the virus. Okay, but yeah, until diarrhea. Yeah. Mm-hmm. So this has been studied for a long time and have verified. They have even found at the time in 1970 and 1980s. We don't know about the coronaviruses, but people have detected the. People have observed viral pneumonia, and the symptom is just exactly the same as Wuhan or SARS. Okay, so Wuhan coronavirus, it changed name many times, and now the official name is COVID-19, and it used to be SARS-CoV-2. Because earlier people think that the Wuhan virus is very closely related to SARS, but it is not. And this is something I want to talk about this morning. So the pandemic now exceeds the size and seriousness of SARS. Sorry about this spelling. In 2003. We still don't know its origin. There are theories, and and that's exactly what I'm going to talk about. Rumors have that it was manufactured in Wuhan P4 lab. They just and Chinese communists is saying that it's originated in a wet market, and where they kill animals and sell the meat right away. So lots of people like food to be fresh, but and so there has lots of cases that the pneumonia or the virus start in some of these local markets. But this time, well, people question that because we still haven't found the patient number 0 or patient number 1. And the report we had is that patient number 1 has no relation with the wet market. Okay, so the virus must go into the market before it came out. Well, that's so there's China has a P4 laboratory, which is the highest secured laboratory, biohazard laboratory, which are qualified to handle all kinds of dangerous biologic stuff. And so they have reported many works on coronaviruses. And there was even a report that they get the coronaviruses and actually change the sequence a little bit. So that caused a big uproar in the West. So it might be that they are working on it and it just happened to leak out. So after the Wuhan virus is spread out wide and far and wide, lots of people have, lots of laboratories try to sequence the viruses. And they are suspecting that the virus is still evolving. And they are suspecting that people have actually taken the viruses and change the sequence a little bit to make it more viral. But it is suspected that the coronaviruses are suspected to evolve quite rapidly. So we have lots of varieties. So I decided that I have the best tools. Okay, so here it is suspected to have evolved in hosts like bat, snakes, and pangolins. Okay. Yeah. So in the report that it's an animal. It's a mammal, but it has scales. It has shell. Okay. And Chinese. It's very prized animal in China because the people think that the scales are medicinal. So they grind up the shell and make Chinese medicine out of it. And reported the Wuhan coronavirus has its genome sequence at 79% similar to SARS. And there's some bat coronavirus it has matched 80%. And especially this particular bat coronaviruses, they reported 96% match. So that's I was kind of suspicious of all these numbers. So I said, well, I have the best tools to look at the sequences and to compare genomes. And so I talked about this exhaustive pattern search algorithm a number of times. And so I'm taking this algorithm and the tools, the code that I have, and I just apply it to the coronaviruses. So what the strategy is to take two viral sequences and compare them. And what I did, because the genome or the genes in a genome, they might locate at different position. So you cannot start from one point and try to compare things sequentially. So my strategy is I'll just take 20 nucleotide sequence from one virus and ask if this 20 nucleotide sequence exists in the other one or not. If it exists, I'll keep this one, and I go to the next one.
Why 20?
Hmm?
Why 20?
Well, that's my magic number. Okay.
How big are these?
30,000. Yeah. I've worked at even several million nucleotides. So this is a potato. Okay, very small genome. So I'm taking 2 and taking 20 nucleotide patterns in one, and just ask if this pattern occurred in the other one. If it does occur, I keep this one. If it does not occur, I put it on another a no match file. Okay, so this way I can scan one and keep all the 20 nucleotide sequences if they do match. So it doesn't matter where this 20 nucleotide pattern is in the other in the other genome. If it exists, I'll just keep it. So this way I have 2 files. One is matches and one is no matches.
You go both ways? You take 20 from this and compare it with this one?
Yeah.
20 from this one?
Yes. That's a separate code. Yeah, yeah, 2 searches. Yeah, you can do forward, backward. I'm doing all of it. So I'm just try to identify sequences which are similar. Okay. Once I find all the code, all the sequences that matches, then I'll pack these sequences, because I'm scanning, moving this 20 nucleotide pattern continually. If they matches continually, then that belongs to same bigger pattern. Okay, so I just pack everything which are consecutive, and then I can see, this whole stretch of sequences have the match on the other one. So I'm finding every possible patterns. And so, here I first, I'm interested in the coronaviruses that's currently reported of the Wuhan virus. Okay, so there's lots of sequences reported in the gene bank. Okay. I just try to look them up and get all the sequences and do the comparison. So you can see these are all supposedly from the same COVID-19, except these 2. Okay. So you can see all the nucleotide. They're kind of different depending upon how you scan it. Okay, and how the computer work. How the computer work doing the scanning, doing the sequencing, and also the assembly. So different people reported different length. Okay, and so and the top one is called the reference sequence. So the gene bank, they accept all donations. When you scan a sequence, you can submit to gene bank. Gene bank would look it over, and if they find that the experiment is acceptable, the data seems to be good, they will include in their gene bank. But they have select one sequence which they consider to be the most reliable one and call it reference sequence. So this top one is the reference sequence. So when I'm matching this all this against the reference sequence. When I'm matching it against itself, of course, it all matches, and the difference is 0. Okay, so if I start to compare it with other, I think I have picked 11 of them, and when I compare this reference sequence with all the other 10, you can see there are 3 of them has no difference, and then there are 6 of them which has a small difference, 40, 40, and this is because if there is a mismatch of one nucleotide, either it has one additional one, it may be missing one, or it has a different nucleotide. And if only one nucleotide different, it would generate 20 patterns, mismatched pattern. Okay. So here, the second one, I have found 60 sequences are different, and that's because there are 3 nucleotides are different. Okay. So 3 and 5, 3 and 3, 2, 2. So this has the sequences has mismatched to up to 5 nucleotides. So this one, I think my interpretation. There are 2 interpretations. Okay, and they might be the difference might be real. If they are real, I think that's what people in India found. When people in India they are comparing 2 Wuhan coronaviruses, and they found 4 nucleotide difference, and they say, these 4 must be engineered. Okay. So people must be going to change these 4 and make the virus more infectious. Okay, so that's what I think one report from India which says that. But I looking at this, I feel that this is interpretation. This conspiracy interpretation. But when you look at this, many of them are identical. Okay, even the length are different, but they don't have any different sequences. And this has only 1, 2, 5 differences. And these differences, if you work at the genome sequence lab, you would know that the computers may report the small differences, and then when you have a 30,000 long genome, you cannot sequence it at once. You have to chop it up into smaller pieces, sequence them, and then assemble them back into the whole thing. So all these things, you may introduce 1 to 5 differences. So that's my thinking. So the difference most likely are due to the sequencing machine, sequencing technology. And then if I compare this Wuhan coronaviruses with SARS and MERS, this Mideast respiratory syndrome, and you can see the difference is huge, and the match is very, very little. So I think from here, the coronavirus is unrelated to these 2 known SARS-like viruses. Okay, and it used to call the coronavirus the SARS-CoV-2 and now they change it to COVID-19. So this is one experiment. I'm just comparing the reported coronavirus sequences and compare them. And I think, from that analysis, I think my tools are working quite well. Okay, so here, COVID-19 is very different from MERS and from SARS. And the three COV sequences are identical. So they show that in different laboratories, they seem to get the same sequence. And I think 6. This is a 6 difference from the reference sequences by less than 6 nucleotide. Okay, I don't know why I put this one, but anyway. So now I'm going out and compare the Wuhan virus against other types of coronavirus. Yes.
Can I ask a question?
Yes.
So on the previous slide,
Yes.
you said the COVID-19 is very close to the reference. So what does that tell you?
The reference sequence is COVID-19.
Oh, okay.
Okay.
Got it.
It's the standard. It's the standard for that virus.
Okay.
So I'm comparing everything else to this reference sequence.
Got it.
Okay. Yeah. Okay. So here, I'm picking up, just in the genome, I'm picking up closely related coronaviruses to COVID-19. Okay. So there are the first 3 are from bats. Okay. Coronaviruses they have found in some bats, I think mostly China. And this one, 229E and NL63 and OC43, these are common cold. These are viruses which cause the common cold. So it was detected very early. And the SARS. And here is a virus found in Hong Kong a couple years ago. It's not a serious problem. Didn't spread very far, but people were aware of it. And the MERS and the SARS. So I have collected all the genome sequences of these coronaviruses. And it's interesting that you can see their length are all very close, 30,000 nucleotide. So I think these viruses share a common property in that they form an envelope, which when you look at the electron microscope, it looks like a crown. Okay. So I'm doing the comparison with one against the other. So this table shows you all the comparisons on all these different viruses. So you can see in the middle that you are comparing a virus against yourself. So this number is generally the sequence minus 20. Okay, because I'm taking 20 patterns to compare. So I'm scanning it, and I have the length minus 20 different patterns to compare with against the other one. And so if we just look at the COVID, and you can see it has the best match is this RATG13, and it is almost half. It has half of the matches. So that's the closest that I can find. And the other two bats are probably very similar to themselves. So you can see the top two, their matches are almost to 20,000 out of the 30,000 sequence, 20,000 matches. So these are probably from two very closely related viruses. And the RATAG has the best match against the COVID. So, the COVID is closely related to one of the bat virus. And it also shared quite a few sequences with the other two bat viruses. And compared to SARS, it has some significant amount of matches, but not enough to say that the SARS are related to COVID. And the other ones has almost no relation. Yes.
So could you say that the COVID was like maybe a researcher could start with the RATG13 and then modify it into the COVID?
It could be. The possibility is there. Okay. Yeah. And it is almost half of the close. But half of the close, I was just saying, well, 20. You ask about why 20. 20 is my magic number, but there's no reason why one should pick 20. So I pick 10. So it has a much shorter comparing, and then the matches is almost more than 20,000. So it shows that depending upon how you do the comparison, this match I'm using very long. 20 nucleotide is a very long sequence. When you compare these two, and they have half of a match, it's very significant in that these two might be they are related, but is it possible for people to change this RATG13 into this one? Nobody knows. But I think I'm looking for the pangolin sequence, but so far it's one group of researchers in Guangdong, and they found that this pangolin, and they claim the sequences matches on 99%, but I haven't seen it, so I don't know. Everybody's waiting for their sequence result. So, from my analysis, COVID genomes are very different from other coronaviruses. Okay, so my result here is very different from what's reported in the news. This one has the best match, but for SARS, especially SARS, has no relation at all. Okay. Okay. It is engineered. Okay. It certainly is possible, but it is most closely related to bat RATG 13. It is so much different from all other coronaviruses that it's unlikely to be engineered. Even the difference between COVID and RATG13 kind of preclude that it's engineered because the difference spread out so much. It will be very difficult to actually engineer it. So it is very difficult to prove either way, whether it's engineered or it is not. It's natural. Okay? If you want to prove it, you have to find the exact sources that they used to assemble the new one. I was watching Scott Adams, the cartoonist, and he was talking about the Wuhan SARS, and he said, well, there's the two explanations. Okay, one is ordinary, which is that the virus get leaked somehow from a laboratory. Okay, and the other one is the virus is engineered. Okay, so you compare these two explanations. The leaking is ordinary. It happens all the time. All the nuclear laboratories, all the top level nuclear research institute, the Berkeley and Los Alamos, and all these laboratory, top secret research laboratory, they all leak. Okay, so leaking is ordinary. It happened all the time, no matter how secure the laboratory is. Engineering is extraordinary. Okay, so to engineer this thing and to make a live virus from one from the other, this is very difficult. And I think the Chinese did some experiment, and they showed some success in being able to modify coronaviruses. But to really make new viruses, a new virus from a group of viruses, and to make sure that it has the desired properties for a weapon, it's very difficult. Okay, so so you want to believe the ordinary explanation or the extraordinary explanation. It's up to you. But so this morning I made some models of the coronaviruses, and so I got the model into my garage, and I said, hey, Bill's coming to talk about all the logs. So I go out and get all my logs ready. And after I get my logs, I forgot to put the models back into the car. But I have pictures. Okay. So here is one colorized electron microgram of a few COVID. And here is another one, not colorized, but it shows the corona around the virus. I have been interested in this corona for a long time. How can this virus be of that shape and with all the coronas around? It has a shell.
Protein shell.
Yes, it has a protein shell, and it has spikes around it. Okay, so the protein, everything's protein. Okay. So I've been interested in, and I think this. So I've always wanted. So here is a much schematic, and I think look at these pictures. It's a fullerene, right? It's a fullerene. It's a Berkminster fullerene. It's a C60 molecule. Okay, 60 carbon molecules form a ball, and so this is one of the. And the COVID, if you look at the genome, what they have, what they decoded, the coronaviruses, and basically they have all the same arrangement of proteins. So there's a big protein. It's a big protein, and there's a few small proteins. Okay, and so this. So they were able to decode the genome and actually assign the proteins. And what I think is, I forgot which one is the. There is an S, the M protein, and there is an S protein, which is the spike. People are most concerned with the spike protein because it's at the outmost of the virus, and it is S protein which allows the virus to attach itself to a cell and actually invade the cell. Okay, but I think this big protein is for the shell, for the inner shell. And so it's a big protein because it has to build a very strong shell to protect the genomes inside.
How do you distinguish between the ones that are coding for proteins and the ones that are coding for control?
There's no control. In the virus. The virus genome is very different from the other living organism. The other organism has the control, but the
cell, it's got to attach itself to the
yes,
DNA.
yes,
Nucleus.
yes, yeah, and it does not require any intelligence. Okay, it just happened. Okay, and this is my theory. The coronaviruses, it has a look of a C60 fullerene or Buckminster fullerene molecule. This molecule has 60 carbons around and which form a ball. And the fullerene is formed from graphite. So if you burn graphite at a very high temperature, and the soot which formed, people found this molecule. Okay. So I think all the graphite has the carbon atoms lying in a sheet. Okay. So when this sheet is treated with high heat, it tends to buckle to form a ball. Okay.
Has anybody counted the spikes on a coronavirus to see if there's 60 of them?
No, it's not 60. Okay. I'll tell you. My thinking is actually 82. Okay. So 60 corners. Each corner has one spike, and in the middle of the hexagonal and pentagon, there's another one. So it has 60 corners, and it has 20 hexagonals and 12 pentagons. Okay, so it's 60 plus 20 plus 12, and that's the number of spikes. And I'll show you why I think so. Yes, yes.
It's interesting you talk about the bucket, the C60, because I recently bought a supplement on Amazon that is just C60 Buckminster Fullerenes. It's
C60 and olive oil.
yeah, and olive oil, and it's a very powerful antioxidant, hundreds of times more powerful than the second runner-up, next runner-up. And somebody told me that when they took it, they felt like 20 years younger.
Yeah,
I don't
it could
want to
be.
be 9 years old again, but I caved and I bought a bottle. It's in the mail now. And, I'm reading about it, and absorbs holds many free radicals and can even go in the middle between the two sides of the strands of DNA.
I see.
Even sitting there, it's small enough to go through there
Uh-huh.
and clear out
Okay.
free radicals.
Okay.
And it doesn't affect anything along the way.
Yes, yes. I think it's very. People are fascinated with this ball,
Yeah.
and I think they feel that this ball you can put lots of vitamin C in it. Okay.
Yeah.
60 plus 20 plus 4 is 92.
Yeah, 92. Yeah.
If you have that nucleotide sequence of 20,
Uh-huh.
does that mean that the possible matches is 4 to the 20th? 4, in other words, combinations.
Yeah, right.
Okay.
So the very
Small number.
yeah. So if you get 20 nuclei to match, there got to be a good reason.
Oh, yeah.
Yeah, it got to be a good reason. So these sequences are matched. Okay, so they are must have some function.
12-9 out there. So 9, 9, 9, 9,
Yes,
9, 9.
yes. You see if you have 20 nucleotide matches, and that's each nucleotide equivalent 2 bits. So it's a 40-bit match. 40-bit match. That's a very tight conditions. Okay. So I'm sorry I couldn't bring you the actual model, but here it is. Yeah. There are 60 carbon atoms, and they're connected that way. That's all. And so. And I'm building another model, which is derived from a hexagonal plan sheet. The graphite is basically this structure. So it is all the atoms are forming hexagonals, but under high heat, the graphite sheet start to buckle, and the way it buckles is some of them the triangle, you lose a triangle, or the triangle collapse, and it forms regular pentagons. If you have these pentagons, and the pentagons are still connected, these edges are still connected, so the whole sheet start to buckle, and 60 is the smallest number that you can form a circular, closed circular structure. So what I did, I took a big sheet of paper and draw all the hexagonals on it, and I start cut out this because I should be just cut out the hexagonals, but at the time I thought, well, I cannot cut the hexagonal that precisely, so I just cut it and remove these things. And if I make lots of hole in it, when I cut this piece, then I would move this one so that this one is on top of it, and then clip on it. stable it. And this way, I can form so this is the paper. I'm cutting it and cutting the hole in the hexagonals. But you just fold it up, staple them together, and so that this hexagonal becomes pentagons. Okay, and that's what I have. I wish I have the models for you. It was, I just staple them together, and this forms a very nice ball. Okay, I want to do the demo. I got a sheet of paper I cut, but I didn't staple it yet. I just want to staple it here, but I can only remember one thing at a time. If I get distracted, I forgot what I have to do. Let me see. So the coronavirus has the look of a C60 fluorine. And fluorine count, yeah, I think this is repeats. Okay, what I want to go back to is to explain to you the spikes. Okay, so here you remove this. Actually, you didn't remove anything. Okay, you just make it. You just make this one. You actually remove this pentagon, this hexagonal. Okay, so you see this sheet. Generally, we think that it is hexagonal. Okay, that's the carbon was very stable in that when it's unsaturated, it forms a hexagonal, a very strong structure. But virus is no graphite, okay, and it forms a fluorine. But how does it form? Okay, so my thinking is that these are the triangles. These are the basic unit for the virus. So if you can make lots of triangles, and if you make the triangles so that they can stick together, and then if 6 of them stick together, you got the hexagonal. But it can happen that the 5 of them stick together, and you have a pentagon. And alternatively, you have the pentagons and hexagonals, and they can form a ball. Okay, and so I think that all these here are all the carbon atoms. Okay, and all the carbon atoms, when they intersect, there's a spike in it on it, and in the middle, if the things are constructed from triangles, in the middle of the hexagonal, you can have a spike as well. Okay, so you can have a spike there. You can have spike in all these intersections, and you can have a spike in the middle of a pentagon. And I think that's how the virus constructs itself. So here, you see, the virus only has to make the triangles. And I think this protein is a triangle. So the virus only has to make the basic to form the fluorine structure. The virus only has to make lots of triangles, and these triangles when they stick together in that way, it can form a ball. Okay, and spike, they are used to infect people. So the structurally is the triangles. So I think the viruses is done. It does not have a program. It does not need a program. So this is a self-assembling. Virus is self-assembling. Just like carbon, the graphite, when you heat it up, it can buckle and form C60 fluorine. Only heat. It only needs heat. It doesn't need anything else to help.
As far as carbon and,
Yeah, it's one of the property.
in the virus, you're sticking together a buckyball, but it's made out of proteins.
Yes.
It's made out of amino acids.
Proteins. Yeah.
Particularly amino acids.
Yeah. Right. So the amino acid has to be it's a long line, okay. But this long line has to fold, and I think it will fold into a triangle. And these triangles have sticking edges, and these sticking edges would glue themselves to each other, and without any intelligence. Okay, so this virus does not need a program. It only needs to make lots of these proteins, and then it will self-assemble into a virus. And this virus has the unfortunate properties that we infect.
So it uses the machinery of the cell to make the proteins that are required to make the triangle.
Yeah. So it only has this RNA stretch, RNA sequence, and then when it invades into a cell, it will conscript the machinery, the protein-producing machinery in a cell to replicate. To make long proteins. And I think one theory has it that the virus genome, when they invade the cell, and it will the translation mechanism. Ribosome. Yeah, the copies, not copies. It has an enzyme to copy itself quite faithfully, and it also uses the ribosome to make a complete string of protein, and the protein was later chopped up.
So each of the triangles is going to take about 100 amino acids.
No, more than that. You see here, you got more than 20K of the nucleotide. So 3 nucleotides translate into amino acid. So the protein is about 1K. I mean 10K. 8 kilo amino acids. 8K amino acids. So the protein is 8K amino acid long. So it's a huge protein, and it has to fold itself. I think if it folds into triangles, and this triangle sticking together, they will form the virus, the coronavirus. Okay, so that's basically what I have. I'm sorry, for I get in the logs and forgot all my models. But you see in the pictures, and that's very very yeah, yes,
So a couple questions.
yes.
Um, what makes it so infectious? Is it those pins on the outside? Number one.
Mm-hmm.
And number two, the this is different than MERS and SARS because you're infectious until up to 24 days before you get the symptoms.
Mm-hmm, mm-hmm.
Usually
Mm-hmm.
you're infectious after the symptoms, which makes it really nasty.
Yeah,
from
yeah,
spreading.
that's very.
So
Yeah.
from your
Yeah.
research?
I think it's the coronaviruses. They have the spikes kind of attach itself to the cell, and then somehow it would once it gets stick to the cell wall, and it kind of break the cell wall and get into the
Is
cell.
SARS a coronavirus?
Hmm?
Is SARS in the
Yeah,
coronavirus?
yes, they are all coronaviruses. But there are other viruses which does not have corona around. Okay,
Yeah, sure.
so
But coronaviruses are very common.
yes, a common cold. They are.
Yeah, and they infect cats in my neighborhood. And it's invariably fatal.
Yeah, cats, chicken, and sometimes pigs. Yeah, so it's quite common. And the other, I forgot your second question. The
So
yeah,
it's infectious up to 24
yeah,
days,
that's right,
which
that's
is
right.
very different
Yeah,
from
yeah,
the
yeah,
other viruses.
yeah.
What makes it do that?
I don't know. Yeah, but my generally observation is that we got cold, we got flu, we got the real flu. So these things you can. My thinking is that some of these viruses attach itself to the nose, and I think it's the temperature. Okay, so lots of viruses they can survive under low temperature. Okay, so when they get into the nose, and nose has a lower temperature. But if the virus is more serious, it can withstand higher temperature, so it can survive inside the nose nasal. And if they can they can withstand higher temperature, it will go to your throat and go to your bronchitis. And then if it is really if it really can withstand lot high heat, it goes into your lung. Okay, so I think the the seriousness of this infection depend upon how virus can survive in your body. So the Wuhan virus is very very nasty. It goes right down into your lung. And generally, if it is less temperature resistant, it would first invade the upper respiratory vessels and start to show the symptom. And then it has a much shorter incubation period. But this one is nasty. So it doesn't even stay in your nose, and it goes directly inside. And I think this is why it is so strong, and so the pandemic is so serious because it goes into your lung. And then after it goes into your lung, it starts to multiply, and then when the symptom shows, the patient is already almost gone.
So you don't think it's possible that this was an engineered virus?
As I said, you need to show that the two or many sources that you engineer it from. But of course, the guy who engineered it would not tell you.
Well, you could engineer it by gene manipulation.
Yes,
You could
yes.
also do it with controlled evolution
Mm-hmm.
and testing
Mm-hmm.
and look for those that are more
Yes.
virulent.
Yes, yes, yes.
And that's quite possible.
Mhm. Yeah, yeah. I think currently the consensus is that the best host for virus evolution is pigs. Okay,
Sounds
pigs.
like bats or
Yeah. Well, the
and they don't live as long as pigs.
yeah, yeah. I don't know. But the generally they're thinking that especially in China, pigs are everywhere, and the chickens are everywhere. So a lot of these animals
But
just
they don't
just
take care of their model organisms.
yes,
They're
they
so
they
big and they eat a lot, and
they are good.
I mean, you're not going to keep 10,000 pigs around just
Uh,
for experiment.
well,
Whereas you
I
can
don't know.
keep 10,000 mites around, because that's what a bat is. A bat is a mouse with wings.
Okay, yeah, yeah. It could be, it could be, it could be. Yeah, yeah. So I think the best model that they have is that the viruses from different sources all are collected in pigs. Pigs does not generally show symptoms. So even with lots of viruses, they still live happily. But when you have lots of viruses in pig's body, they tend to cross. So if they are multiplying in pig cell, and in the process of multiplying, they might get mixed.
Maybe it is a good model organism.
Yeah, it is. It is. Yeah. But I don't know. Okay. Yeah. Thank you very much. Okay. All right. We'll go lunch and see you in the afternoon.
The weather service says it's a very lovely 65 outside.